to go through section 1 physics to go. Starting with number 1, you push a ball to start it rolling on a perfectly friction surface. How far will the ball roll? Well, if it's perfectly frictionless, then Newton's first law of motion, the law of inertia, tells us that this ball will continue to roll forever and ever. Explain your answer using Newton's first law. Newton's first law tells us that an object in motion will stay in motion, an object at rest will stay at rest. Number 2, a ball is released from a vertical height of 20 centimeters. It rolls down a perfectly frictionless ramp and up a similar ramp. What vertical height on the second ramp will the ball reach? So this is just like from the reading where we had Galileo's thought experiment, where if you took this marble and you rolled it down a frictionless surface, it's going to come back up and return to the same surface, just like we did in the investigate. Because it is perfectly frictionless, if we release a marble here, it's going to go down and it's going to come back up to the same exact height. Number 3, do you think it's possible to arrange the conditions in the real world to have an object move unassisted in a straight line at a constant speed forever? Okay, so for it to move forever and ever, basically you have to remove all friction. So the closest we've come, pretty close to removing all friction. You could think of ice as being nearly frictionless, but it's not. Something really interesting happens when you have an ice skater's blade. This is like the head-on view in contact with the ice. The ice is melting ahead of the blade. So it's not like ice is being glided on, but instead you're going through water. So you are experiencing some resistive force there. So no, not possible. Number 4. Use what you have learned in this section to describe the motion of a hockey puck between the instant the puck leaves a player's stick and the instant it hits something. No slap shot allowed. The puck must remain in contact with the ice. Alright, so I would say, just like I said, the ice exerts almost no frictional force on the hockey puck. The puck is going to glide basically with a constant speed in a straight line until something else acts on it, right? Newton's first law tells us that an object in motion will stay in motion, an object at rest will stay at rest until an unbalanced force acts on it. So just a quick word about that. An unbalanced force, if I think about a box, that box is sitting on a surface, then if I look at the forces acting on that box, we have the force of gravity, the object's weight, mass times acceleration due to gravity, and then we have the normal force, which is equal but opposite to the force of gravity. That box will stay there forever and ever until somebody comes along and they kick it. Once they kick that box, now we have an unbalanced force. So we had our normal force being balanced and canceled out by our force of gravity. Now we have this unbalanced force. That's what gets an object to start moving or to stop moving. So we have the hockey puck gliding along a straight speed at a constant, or straight line at a constant velocity. If the hockey stick exerts a force on it, well, now that hockey puck is going to either slow down or stop, or maybe it's going to be shot off in the other direction. So once this force is applied here, the force of the stick onto the puck, that's when things start happening. Number 5, the speed relative to the person. You are riding a bike and steadily pulling your little brother in his red wagon while someone standing watches you and your brother go by. So we got the wagon with your little brother attached to your bicycle. Which you are happily pedaling away. He has a ball and throws the ball forward. So your little brother has a ball and throws the ball forward. Now remember, we're thinking about this as somebody just off to the side. This is the back of somebody's head. Just watching this happen. So your little brother throws this ball forward at a velocity of 2.5 meters per second relative to his body. So we're taking it from here to forward 2.5 seconds. While you're pulling the velocity at 4.5 meters per second. At what speed does the person who is standing nearby see the ball go? So just like when the section was talking about a running start in sports like baseball or javelin, the javelin was being launched forward with some velocity, and that velocity is the velocity of the girl's hand plus the velocity of her shoulder plus the whole body, and that's why you want to take a running start to get a ball moving faster. So football, quarterback could be running forward and running forward out of the pocket and then throws it. That ball's going to be coming off the hands a little bit quicker than it normally would. Okay, because all of the speeds are added up. They're all moving in the same direction. So the same thing's going to happen here. We're just going to add up these speeds in the same direction. So we have 2.5 plus 4.5. It should be 7 meters per second is what it apparently seems like the ball is moving. You experience this when you're driving in traffic. When you're driving along and you're going 70 miles an hour and somebody passes right by you, then you know instinctively that they're going faster than you. Meanwhile, the people in the oncoming traffic appear to really be zooming by because they are going this way plus you are going that way, so it seems like the oncoming traffic is moving a lot faster. Zooming by, hard to see, especially on the highway. Number 6. A track and field athlete is running forward with a javelin at a velocity of 4.2 meters per second. If he throws the javelin at a velocity relative to him at 10.3 meters per second, what is the velocity relative to the ground? So back to relative motion. So he throws this javelin in that direction at a speed of 4.2 meters per second. Meanwhile, he himself is running in this direction at a speed of 10.3 meters per second. Well, relative to the ground that's staying still, we're just going to add those two together, just like we did in the last problem, and we're going to get 10 plus 4 is 14.5 meters per second. Number 7, a two-parter. The infamous two-parters. You are riding a train. Since the train car is almost empty, you and your friend are pushing a low-friction cart back and forth between the front and the rear of the car. The train is moving at a speed of 5.6 meters per second. Suppose you push the cart forward toward each other at 2.4 meters per second. What is the velocity of the cart relative to the ground when the cart is moving toward the front of the car? Okay, so because you are on this train, I don't know what that's supposed to be, but you're here and you roll this smaller cart forward to the other person over here. then you are wondering relative to the ground. Well, here we are again, the ground is not moving. Okay, so the relative velocity is going to be the speed of the train, plus the speed that you roll the cart. So we have 5.6 plus 2.4, 4 plus 6 is 10. That should equal 8 meters per second. Now we're going to switch it up. I'm going to keep this main diagram. And now we're wondering if the cart is going in the opposite direction of the train. So velocity of the train in this direction, and now we have the cart moving in this direction at the same speed, 2.4 meters per second. The train is 5.6 meters per second. So now that they're moving in opposite directions, you're going to do just what you think we're going to do. 5.6 minus 2.4 equals 3.2 meters per second. So that cart would actually look like it is going slower to somebody standing off. That is relative motion. All right, part C. What if you and your friend push the cart perpendicular to the aisle as the train moves forward? This is a more complicated situation. What is the cart's velocity relative to the ground? Okay, so we have the train moving in this direction, and then you push the cart in this direction. We want to know the relative velocity, perpendicular to each other, right? So this is going to be 2.4, and this is going to be 5.6. Well, this is a vector. Velocity is a vector. That's an arrow that shows magnitude and direction. And with that vector, we can pick it up and we can move it parallel as long as we don't change the angle. So by taking that vector over there, this is 2.4. Now, relative to the ground below us, this is what our motion is going to look like. Another common way to think about this is if you're on the bank of a really fast river and you need to swim across the river, well, you have to angle yourself backwards if the river's flowing in that direction, so that way you can go straight. Same situation. Oh, not same situation, but same kind of thing. Okay, so right triangle, hooray. This is just Pythagorean Theorem. 2.4 squared plus 5.6 squared is going to equal to c squared. Square root of all of that, and then that goes away. And then I get the calculator. So it's going to be the square root of 37.212. In math class, you may leave it like that. In physics class, I would say just go ahead and hit that enter button. And that will give you 6.09 meters per second. So that was number 7. Number 8. Let's see. While riding a horse, a competitor shoots an arrow horizontally toward a target. So it sounds like the horse going this way, and the arrow is going to go that way. The speed of the arrow relative to the ground as it reaches the target is 85 meters per second. If the horse was traveling at 18 meters per second, at what speed did the arrow leave the bow? So I'm going to move this vector over here, and really I'm going to shorten this one because that's the smaller speed, this is the bigger speed, 85 meters per second, and we're just going to find out whatever that is. So right, if the horse was traveling at 18 meters, what speed did the arrow leave the bow? Oh no. we need to figure out what was the speed down here relative to the ground. So to do that, it's going to be your 85 minus the normal 18. Sounds like I assumed they were perpendicular to each other, but it's got to be that the arrow is going in that direction. I'm riding a horse. Question could have been worded better. 67 meters per second. That's 8. Number 9. Ball is released at a ramp with a vertical height of 15 centimeters. So that's 15 centimeters. Remember to convert that to 0.15 meters. Calculate how far up the second ramp the ball will roll if the angle of the second ramp is 45 degrees, 20 degrees, 15 degrees, and 5 degrees. So at different angles. So this is just going to use some trigonometry or geometry. SOHCAHTOA. Right. So we just want to see if it's going to be released from here. How high is it going to go up on the other side? And the first thing that you're going to have to do